Good evening, everybody. Welcome to Chems 170 with your host, me, Dr. White. Hi, everybody. Tonight I'll be doing the review for test number 1, which I'll be giving this Thursday. On Thursday morning at about 8 or maybe even earlier, I will send out a password in an email to each of you that will allow you to open the password protected file in the assignment area of D2L, which will be test number 1. I like those special effects. Uh-oh, it's bad humor night. But anyways, I'll do that. You'll have until Friday, I forgot what time, Friday late afternoon, early evening, to hand in test number 1. Remember, upload it as a single PDF file, hopefully like you've been doing the labs or the lab that's due this week. And then by Sunday, 1 p.m. at the latest, I will have test number 1 graded, and I will send out to each of you an individual email with the number of points for each answer you had on test number 1. A week from, maybe less than a week from tonight, next Monday night at 8 p.m., I will go through test number 1, all the answers on Zoom, and I'll send out an announcement about that. If you can't make it, I'll videotape it so you can watch it on my YouTube channel. So let's get started. And remember, in my class, there's no such thing as a dumb question, so always feel free to ask questions. Now, what you see on the screen, test number 1 review by me, Dr. White, is available to you in the lecture folder of D2L, cleverly named test number 1 review. It's both as a Word file and a PDF file. So let's go through this. Things you should know for test number 1. By the way, I should mention, test number 1 will have no multiple choice. I don't like multiple choice. I hated them when I was a student. And it'll have 3 main parts or type of questions. One is general knowledge. Next, nomenclature, which is names. I'll go over a lot of that tonight. And finally, reactions. And what do I mean by general knowledge? Well, how many bonds to carbon? I like that nonverbal communication. 4, that's general knowledge. Or, did you remember when you drove by a gas station that gasoline contains alkanes? All right, let's get going. Now, let me just check one. Yep, I'm recording this. Once in a while, I forget to turn the recording on, but it's on. All right, you should know what's a hydrocarbon. That's a molecule or the molecules with only carbon and hydrogen atoms. There are 2 types of hydrocarbons, saturated and unsaturated. And you should know that a saturated hydrocarbon is a molecule with only carbon and hydrogen atoms. That's a hydrocarbon. But being a saturated hydrocarbon, it has only carbon-carbon single bonds. All the carbon-carbon bonds are single bonds. And an unsaturated hydrocarbon, being a hydrocarbon, is a molecule with only carbon and hydrogen atoms, and it contains 1 or more carbon-carbon multiple bond, or you could say 1 or more carbon double or triple bond. Now, I won't ask you what's an alkane, but we talked about acyclic saturated hydrocarbons, cycloalkanes, which Dr. White and Mother Nature love, are ooh, that's a mistake. Are cyclic saturated hydrocarbons. Now, you should know how to draw alkanes and cycloalkanes, and I'll show you that in a second. Now, next I talk about, and hopefully you've been watching the videos, IUPAC. And I'll never ask you what IUPAC stands for, even though I like to say it because it sounds cool. International Union of Pure Applied Chemistry, and that's the organization that set up the nomenclature rules, which are naming rules. And you should know how to use that. Now, in order to do that, and we'll do one example or two tonight, you need to know the alkanes 1 through 10. And what do I mean by that? This table, which is the lecture section found in the lecture section of D2L, called alkanes, IUPAC names, you should know methane 1, ethane 2, so on, propane 3, carbons, pentane 5, hexane 6, octane 8, octane number like in gasoline, and nonane 9, decane 10. So you should know these. Hopefully you've learned it by now. Also, there are key alkyl groups you should know. And this is also in a file in the lecture section of D2L called Key Alkyl Groups, both as a Word document and a PDF. And my favorite, methyl, ethyl, and propyl, not quite laws, isopropyl. They've been good to me, and I've been good to them. And butyl and tert or T-butyl, which I really like. They've been good to me too, the T-butyl group. And you should know these. And the line means when you have CH3 bond to something else, that's called a methyl group. When you have 3 carbons and the center carbon is bonded to something else, that's an isopropyl. And the first thing would be, and let me change this. All right. In order to name this, and this is a nomenclature question, I could ask, give the IUPAC name. For the following. Say one of the questions would be this structure. Well, how do you do that? You have to find what is the longest continuous chain in this molecule. And if you've watched the videos, you've seen me do that. And I could start from here, 1, 2, 3, 4, 5, 6, 7. That's one chain. 1, 2, 3, 4, 5. That's another chain. 1, 2, 3, 4, 5, 6. And as I've said, the math in this class is very hard. You have to know how to count to 10, know what numbers from 1 to 10, what ones are larger and smaller than the other. And the largest number is 7. So the longest chain, let me clean this up for a second. Is 7 carbons. And you've learned table with the alkane name, 7 carbons is heptane. Now, as soon as we say that, this is all spoken for, 7 carbons. But are we done? No. You have this group, alkyl group, and this one. And here we have my favorite, a methyl group, and hopefully it's your good friend by now, and 2 carbons is ethyl. Now, remember I said in the video, and I'll say it again, I'm not going to hold you to the IUPAC alphabetical rule, but I will hold myself to it. So this would be ethyl and methyl. Now, what carbons are the 2 alkyl groups on? When you number, and listen carefully, you always start from the end of a chain. Always start from the end of a chain. Students want to say, oh, this is the first one, I'll make this carbon 1. No, you have to start from the end of the chain. If we start here, this is on carbon 2, this is on carbon 4. If we go the other way, 1, 2, 3, 4, 5, 6, then the alkyl groups are on 4 and 6. And you start from the end that gives the alkyl groups the lower number. So therefore, based on that, we have the ethyl group is on carbon 4, the methyl group is on carbon 2. So that'd be 4-ethyl 2-methyl heptane. Now, bad habit I have when I print is I sometimes capitalize things and you don't. All those should be lowercase, but on a test, I'm not going to take off because I don't follow it. If you print some of it all caps, some whatever, just make sure I can read it. You don't want me guessing. What the heck is that? All right, that's one type of nomenclature question. The other is draw the structure. And hopefully you've done the problem set. So this is just mainly a review for you. And let's do one. Would be 1-ethyl 2,4-diisopropyl cyclohexane. So how do you do this? Well, you always start from the right and move left. Hexane. You've learned that table, 6 carbons. But wait, we have the prefix 6, and that means it's a ring. And a ring with 6 carbons, which Dr. White loves, and so does Mother Nature, is this. On carbon 1 is an ethyl group. And you can have these carbons going like I have to this way. You can do it this way. You rarely do it up, but you could. Now, on carbons 2 and 3, di is the prefix for 2. Tri is 3. In this class, and in my years, decades in the chemical industry, I've never seen higher. Tetra is 4, penta is 5. I've never seen that, but I'm sure somebody has made that. So di means there's 2 isopropyl groups, and they're on carbons 2 and 4. And you've learned an isopropyl group is 3 carbons, and the center carbon is attached to, in this case, the ring. Now, you know there are four, four bonds to carbon. So this carbon has one bond, 4 minus 1, 3 hydrogens. This carbon has three bonds. So 4 minus 3 is 1. And this carbon down here has one bond, 4 minus 3, 4 minus 1 is 3. And the same thing over here. And that's another type of nomenclature problem. And here again, I give you the different alkyl groups. Now, one of the things I've done teaching this class is I could do it all theoretical, and guess what? That wouldn't be too much fun. And organic chemistry should be fun. Don't forget, I'm an organic chemist, I'm biased. So throughout the semester, you'll see, and I spelled this wrong too. But anyways, I was always first down in spelling bee. But you should know real world uses of the different things I talk about. And where would you find an alkane? Natural gas, what you use to cook, that's methane. Propane for your barbecue, that's an alkane. I already mentioned gasoline, Vaseline, baby oil, and 50% of the weight of a candle is or are alkanes. I didn't bring any up, but when I used to work for these two Dutch companies, one of them, I spent a lot of time in the Dutch city of, Americans pronounce it Gouda, where the cheese comes from, but it's really pronounced Gouda. And in that town, in the town center near the big cheese stores, and they have some big ones there. Whoa, you can buy big wheels of cheese. I forgot how many, 20, 30, 40, 50 pounds. But anyways, they had a very small candle shop that made hand-dipped candles, and I have a bunch of them in my collection at home. All right. Now, in this chapter, there was only one reaction I asked you to learn, and I taught the concept of a general reaction. And here, if you have any alkane, and also it's true for cycloalkane, and you react it with oxygen, organic chemists, unless you have to figure out charge weights, how much to react of different things to make something, which we don't do in this class, we're only interested in what do you make? And here, the products are carbon dioxide, CO2, and water. Now, a chemical product is heat, which is the most important thing. And I will never ask you to balance an equation in this class. So if I were to ask you, give the product or products for the following reaction, what do? You look at this and you say that's an alkane. And O2, I hope you all know, is oxygen gas. You've memorized this general reaction, and that gives you CO2 plus water. And so the answer would be CO2 plus water. If I had another alkane like octane, like in your car engine, you'd get CO2 and water. And that's what I mean by a reaction. I see there's a question. And hopefully I'm pronouncing your name right, Dorcas.
Yes. My question is for the test. Do you want us to add the heat, or you want us to just put the...
I will just ask for chemical products.
Oh, okay.
If you want to put down the heat, that's fine.
Okay, great. Thank
No,
you.
that's fine with me too, but you better get the CO2 and water. And as I keep on saying in my videos, There's no such thing as a dumb question. That's a good question.
Oh, thank you.
One thing I should mention, when I grade a test, I don't sit down and say, all right, how many points can I take away from these students? No, if it's right, it's right. If it's sort of right, I'll try and give you, it's hard in organic chemistry, unlike general chemistry where you're solving problems with math, to give partial credit, but I'm not there to try, oh, you forgot that was too far from this carbon, that carbon. I'm going to take off. No, I don't do that. I'm trying to be in your corner, but I'll be honest. If it's wrong, it's wrong. Does that help?
Yes, excellent. Thank you.
You're welcome. All right. Let's move on. The next thing I talked about were the alkenes and the alkynes. Now, an alkene, the ene ending, tells you have a double bond. Remember, double bond is two bonds between two carbons. And you should know one of those bonds is called a pi bond and the other is a sigma. As you see later on, I can break pi bonds like that. Sigma, you don't. In fact, single bonds, sigma bonds, you almost never break except in combustion, which we just showed in another reaction, which I don't teach in this class. Now, an alkyne is a triple bond. And a triple bond, you should know, has two pi bonds and one sigma bond. Now, let's go through the IUPAC names. For an alkene, a molecule with a double bond, you name the longest chain as an alkane. You name the longest chain as an alkane. Then you drop the ane ending because there's a double bond, and you replace it with an ene ending. For acyclic alkenes, you need a number. Which carbon is the lead carbon closest to the end of the chain? And that gets priority always. And if needed, cis and trans, and I'll show you that in a little while. If it's in a ring, the rings I've encountered, they're always going to be cis. In reality, you could make a larger ring, but I think decades ago I saw one paper, but in real life, it doesn't exist. So you don't put cis or trans. And if it's the only functional group, which is how I teach this course, that one of the carbons of the double bond ring is always one, and you don't have to put that down. And the question is, what's the IUPAC name for this? From now on, when you look at a molecule, you should look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond should get your attention like this. That gets your attention. And here we have a double bond. And that's an alkene. How many carbons in the longest chain with the double bond? 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, 6. And the answer is 6 is greater than 5. So 6 is hexane. But the ane ending, you drop and you put ene hexene. Now, one of these two carbons is going to be the one that's closest to the end of the chain, lowest number. And notice this would be this carbon. So it's 2-hexene. That tells you the lead carbon is carbon 2. Now, if you have two different groups that are the same, or two groups that are the same on each carbon of the double bond, you have to worry about cis and trans. And what you do, in this case, hydrogens, in my class, I stick to hydrogens. Oops, I gave that away. If I had a mirror or a pencil or a line going across here, or a plane, notice these hydrogens are on the opposite side, trans. If they were on the same side, below or top, that would be cis. So that would be trans 2-hexene. Remember, there are 6 carbons, 4, 5, 6. Now, as soon as I say trans 2-hexene, all that is spoken for. Are we done? Oh, no. We have our good friend, the methyl group. And that's on carbon 4. And that's how you do double bonds. Now, if they're in a ring, you won't have cis or trans. Now, this is a 5-member ring. And notice we have a double bond. And how would you name that? You have a ring, 5 carbons. Remember, every bend in a line is a carbon. And here we have cyclo. Remember, when you're writing the name of a ring, don't forget the word cyclo. I had a student lose years ago 12 points on a test because she forgot to put cyclo, and I'll mark it wrong. And it's pentane, but it's a double bond. So you drop the ANE, pentene. One of the 2 carbons has to be 1, the other has to be 2. So we don't have it. Oh, look, we have our old friend, the methyl group. Now, the question is, what carbon is it on? One way to number it is that way. Remember, one of the 2 carbons has to be 1, the other has to be 2. So you number in the way that the alkyl groups have the lowest number. And you have a choice, 3 or 5. Which is the lowest number? And time's up. Hopefully you pick 3. And that would be 3-methylcyclopentene. Now, triple bonds are a lot easier. If you have a triple bond, remember that's 3 lines between 2 carbons. You find the longest chain with the triple bond, and you drop the A and the ending, name it as an alkane, and this is wrong too. Boy, I've got to go back and correct this thing. I apologize. And you put YNE and a number. One of the carbons in the triple bond will always have the lowest number closest to the end of the chain. And in a triple bond, you cannot have cis or trans. And I think only once in the last, well, I hate to say this, 30, 40 years that I see, and this was like 34 years ago, maybe longer, I saw a paper where they had a triple bond in a ring. You don't see that in real life, and even the chemical industry stuff, it really doesn't, and I won't have that. All right, now we start talking about the fun part of organic chemistry, reactions. And I showed you general reactions. And whenever you see a double bond in a molecule, 2 lines between a carbon, and if you add hydrogen and a catalyst, and the catalyst can be nickel, platinum, or palladium, you break the pi bond, and each carbon of the double bond gets a hydrogen. Do you break carbon-carbon single bonds? No. So let's take a look at this. And if I were to put this on the test and say 3 points each, now for this problem, and most of them I will ask, give the organic product or products for, and this would be say A. Well, how do you do that? Well, you look at a molecule and you look for what's different, and that should get your attention like this. Ooh, or like that. And we have a double bond. And nothing else is a functional group. And therefore, all I see now is a double bond. What am I reacting with? Hydrogen, and platinum is a catalyst. And the catalyst in our case is platinum, but it could have been palladium or nickel. In industry, we use nickel because it's cheaper. And you break the pi bond. Remember, double bond has 1 pi bond and 1 sigma bond. And each carbon of the double bond gets a hydrogen. Now, do you break carbon-carbon single bonds, except for combustion in my class? No. Remember that. Hold on, time out for a public service announcement from the management me. For all my tests, 2 things you should know. One is how many bonds to carbon? 4. Boy, I gotta get that finger fixed. 4. 4 bonds to carbon. And do you break carbon-carbon single bonds except for combustion? No. I'll say that again. Except for combustion, do you break carbon-carbon single bonds in my class? No. Even at my level, a PhD, breaking carbon-carbon single bonds is a rare reaction. You don't. So if we look at this reaction, we start out with 5 carbons, 4 across, and this methyl or carbon there, because you don't break carbon-carbon single bonds. Now there's a pi bond here that I do break, and I did. And here are the 2 carbons of the double bond, which become these 2 carbons, which are these 2. Now each one gets a hydrogen, because that's what our general reaction shows. And I know there are 4 bonds to carbon, so I can put in the hydrogens. Now, to make your life easier, don't tell anybody I'm being nice. I don't do what certain instructors do, saying, well, this hydrogen is on that carbon, it should be CH2. This hydrogen is on that carbon, it should be CH3. If you want to write the structure this way, either one of these would be correct. This would be a little closer right here, but anyways, but this way is one less step for you to mess up, so that's why I'm being nice. And that's how you do general reactions. Now, a question students usually ask is, when I am given this problem, do I have to write the general reaction underneath? And the answer is no. But as I've said in the video, I'm pretty sure I have, some of my best students in Chem 170 I've ever had, underneath every one of these type of reaction problems, always write the general reaction. And I'll also say some of the best students I've ever had in Chem 170 never write it. Whatever helps you, do it. I do that, but it's in my brain. I think it's right here. It's cemented in. So all the general reactions. This class, I think years ago, one student counted, I think there are about 52 general reactions I teach you. I know about 450, 500 general reactions. Do I know them all? No, but I know a lot. All right. Now, let's go back to general reactions, and I'm not going to do an example for each one of these. I've done it in the videos. When you have a double bond and react it with halogen gas, remember X is the variable we use, or the way we show halogens, fluorine, chlorine, bromine, or iodine. You break the pi bond, and each carbon double bond gets a halogen. Remember, you don't break carbon-carbon single bonds. Now, these two are symmetrical addition. You're adding the same thing to both carbon of the double bond. What if it's unsymmetrical? And this case, if I take a double bond, add HX, where X in this case could be chlorine, bromine, or iodine. Why not fluorine? Hydrofluoric acid is probably one of the most dangerous chemicals around. In fact, all the years I did chemistry, when I was a bench chemist at this one company, I was asked to do research with HF, and I said no. That's the only time I've ever, because I knew how dangerous, and I didn't want no part of that. The person, they finally got stuck with that, and I shouldn't be laughing, almost had a nervous breakdown because how dangerous it is working. Anyways, you have a double bond, HX, you break the pi bond, one carbon gets H, the other gets X, and it follows Markovnikov's rule. What's that? Markovnikov's rule is the carbon of the double bond with the most hydrogens gets the hydrogen from HX. Oops. And the other carbon gets the halogen. So if I were to ask you, give the organic product or product 3 points each for the following reaction, what do you do? Well, you look for what's different. What's that, a carbon-carbon single bond or a carbon or a hydrogen atom should get your attention? Double bond. Nothing else is going to react with HX or HI. Now, iodine is the halogen, so this is really HX, where X in this reaction, it can be chlorine, bromine, or in our case, iodine. And you've learned this general reaction. Remember, I say, write it down 5 times and say it out loud, and that's a good way to memorize it. Works better than flashcards for most of my students and me too when I was a student. You break the pi bond, one carbon gets the hydrogen, one carbon gets the halogen, and it follows Markovnikov's rule, M's rule. So we have these 2 carbons. Do we break carbon-carbon single bonds? No, so we're going to end up with 3. We started with 3. Now, my 2 carbons of double bond, this carbon has 2 hydrogens, this has 1. Now you have to use your high-level math skills. Which one has more hydrogens? Hopefully I'll pick 2. So Markovnikov's rule, Remember, I learned it, the rich get richer and the poor get poorer when we're talking about hydrogens. This carbon will get the hydrogen. This carbon will get the halogen. What's X? Iodine. Now I know there are 4 bonds to carbon. And that's how you do it. Remember Markovnikov's rule. The carbon of the double bond that has the most hydrogens, in this case 2, gets the hydrogen. The other carbon gets, in this case, the halogen X. Now, another example of Markovnikov's rule is hydration of an alkene. I never asked you to learn reaction names. A double bond, H plus. In organic chemistry, H plus means acid catalyst. Remember, acid is a proton donor, H plus, that's why we use that as general. And then usually sulfuric acid or other acids, which I'm not going to cover in this class, like methane sulfonic acid I've used, or toluene sulfonic acid. I've used that too in real world. And water. Think of water as HOH. You break the pi bond. A catalyst is something that makes it go quicker, but is not consumed or added in the reaction. And therefore, you break the pi bond. 1 carbon of the double bond gets H, the other gets OH, and it follows Markovnikov's rule. The carbon of the double bond with the most hydrogen gets the H, and the other carbon gets the OH hydroxyl group. Now, we moved on to triple bonds. Remember, a triple bond has 2 pi bonds here and 1 sigma. So I can break both of those. Well, organic chemists are lazy. And if we don't want to balance it, how can we show we need more hydrogen? Because you need 2 molecules or 2 moles of hydrogen. Well, we used in letters X and S in a bracket, and that means excess. You have, in this case, all the hydrogen in the world that can react with a triple bond. And now we don't have to balance it or even show us something balanced. Remember, use a catalyst, nickel, platinum, or palladium to break the pi bond. But now there are 2 of them. So each carbon of the double bond gets not 1, but 2 hydrogens. And the same thing happens with halogenation. Triple bond, 2 pi bonds, halogen gas, remember X in this case, fluorine, bromine, chlorine, or iodine, and each carbon of the triple bond, since you have 2 pi bonds, gets 2 halogens, or a total of 4. And some of these reactions I've mentioned, when you put halogens on a molecule, you make it more flame or flame retardant. You can never make anything flame proof that could burn. Eventually it will. You know something? I haven't shared the fun tonight. So why don't you try this one? Give the organic product or products for the following. Your turn. And when you're done, give me a thumbs up so I know you're done. Thank you, Elizabeth. Thank you, Abigail. Thank you, Chris. We'll give everybody time. Thank you, Roxanne. And be patient. I try and give everybody time to finish. Also allows me to sneak some water in. All right, let's get going. So how do you do this problem? How do you figure out what is the organic product or products? You look for something different. What's not carbon, what's not hydrogen, what's not carbon-carbon single bond? Should get your attention like that. Ooh, a triple bond. So immediately I know I have a triple bond. I'm reacting with bromine gas, which is halogen gas, and notice I have excess. And I've learned the general reaction where X can be fluorine, chlorine, bromine, or iodine. And remember, this has 2 pi bonds and 1 sigma single bond. I can break the 2 pi bonds like that. Oh, it's broken tonight. And each carbon of the triple bond gets not 1, but 2 halogens. And therefore, do I break carbon-carbon single bonds? No. So I start with 4 carbons. I better end up with 4 carbons. Now, this is important. These are the 2 carbons of the triple bond, which are these. And where you place things in a molecule makes a difference whether it's right or wrong. If you were taking anatomy and you were to draw the face and you put the nose up here, you'd probably get marked wrong. I don't know, I've never taken anatomy and physiology, but I guess that, and a lot of you might or have. So each carbon gets not 1, but 2 halogens. It's bromine. And each one of these counts as a bond to carbon. I know there are 4 bonds to carbon. And I'll put in the rest of the hydrogens and I'm done. And that's how you do it. Next, let's talk about aromatic compounds. And there are 2 of them. You should know the IUPAC name, which is the common name in certain cases. Chris, do you have a question?
Yeah, for the one we just did, I wrote in front of the C BR2. Is that fine, or can we not do that?
Hold on. I try and stay away from shorthand because students get confused. But did you do this?
Yeah, yeah.
Guess what? That's correct too.
Okay.
I would normally, if I were talking to other PhD chemists, organic chemists would do the bottom. But for this class, I try and do it stepwise so you can see where it's going and understand it better. Because sometimes students get confused when I do that, where this makes it clear. But on a test, did I tell you I'm this close to the person who's grading the test? Me. I can take either one would be correct. Again, as I mentioned earlier, I'm not saying you have to do it only one way. If it's correct, in this case, both are, you can do both ways, okay?
Okay, thank you.
You're welcome. All questions are good questions. All right, back to aromatic compounds. And you should know benzene is a 6-membered ring with 3 conjugated double bonds, meaning alternating single or double single, double single, double single, single, alternating. And you can draw it this way or this way. Now, there's another way of drawing benzene, where you use a circle instead of showing the double bonds, because that's the pi electrons holding hands. And I like the first two ways because I just think it looks cooler. But on my test, you can do it any way of those three. So if I ask, draw the structure of benzene, it's a 6-membered ring with 3 double bonds conjugated. Over 1 year, student on test 1 drew all her benzene rings like this. This is not benzene, this is cyclohexane. I marked it wrong. I think she lost 15 points. She would have gotten a high in the 90s and she didn't. Oh, is she mad? And I explained. I mentioned it. This is cyclohexane. This is benzene. Next, if there's a methyl group on a benzene ring, again, this name comes from eons ago. They called toluene. And IUPAC in their infinite wisdom, and I mean that, said, we're not going to get those organic chemists to change. We'll call that, use the same name, toluene. Again, don't forget to put the bonds inside the ring. And here, I really should have written it this way. You can write with the circle, I don't. You can say, oh, I don't. I thought I did, and I don't. Now, important thing, the methyl group counts as a substitution on the ring, and I'll explain why. Now, at this point, I introduce you to some more substituents that you should know. Cl is called a chloro group. F is fluoro, Br bromo, I is iodo, and NO2, where the bond is from nitrogen to the benzene ring, or the aromatic ring, is called the nitro group. And I talked about dye substitution. The names most people use instead of numbers is ortho, meta, and para. Ortho is 1,2 disubstituted benzene ring, or toluene. Meta is 1,3. Para is 1,4. And if I were to ask you, give the IUPAC name of the following, and you look at that and you say, oh, look, what's different? A ring with 3 double bonds conjugated. That's benzene. It has a chlorine on there and a bromine. So that would be bromo, because Br is bromo, Cl is chloro. Now, it doesn't matter in this case which one you call 1. And if I did it the other way, remember you go in the direction clockwise or counterclockwise, give the lowest numbers. Both of those are 1,3 disubstituted. 1, 3. And if we go back to the other chart, 1, 3 would be meta. So this would be meta-bromochlorobenzene. Now, since I am not holding you, don't tell anybody, I'm being nice. I'm not holding you to the IUPAC alphabetical. If you put down metachlorobromobenzene, I'd mark it correct also. Now, let's look at toluene. Now, toluene, the methyl group counts as a substituent, but it's always considered 1. So this is 1, 2, 3, 4. toluene. NO2 is the nitro group. And 1,4-disubstituted is para. So this would be para nitrotoluene. Now, if you have more than 2 groups on a ring, then you use numbers. Remember, I went through the one nitroglycerin. Oh, I have to do this. Everybody know what that is? It's paramedic. You can all boo. 1,4 paramedic. Never mind. Well, if you like that one, I forgot to mention earlier, everybody know what that is? Transparent. The hydrogens are trans and then parent. Never mind. Well, I'm getting all the bad jokes out tonight. Now, important thing about a benzene ring. The double bonds are holding hands. The pi electrons are conjugated. And this I'm not going to ask you on a test. They're in a p orbital. And they're all connected together holding hands. Sort of like Ring Around the Rosie. Never mind. But anyways, that gives benzene and aromatic compounds added stability. They're much more stable than if you theoretically calculated a cyclohexane ring with 3 double bonds in it. And therefore, you're not going to, in reactions of aromatic compounds, you do not break those bonds. What you do is you substitute one of the hydrogens. Remember, on this carbon and every one here in benzene, there's a hydrogen, we just don't show it, with something that you react it with. Now, if we look at the first reaction, halogenation, you take halogen gas, or in real life, X is chlorine or bromine, and you need a catalyst for this, ferric trihalide. And what happens is you replace one of the hydrogens with a halogen. And the question B, give the organic product or products are the following. We look here, what's different? Ooh, a benzene ring. Cyclohexane with 3 double bonds. Then Br2 halogen gas. Ooh, a catalyst. Ferric trihalide. X in real life can be chlorine or bromine. I've never seen it with iodine or fluorine. And you replace one of the hydrogens with a halogen. In this case, what's X? Bromine. Now, watch closely. And here's where the student one semester lost a lot of points. This was her answer. This is bromo cyclohexane, not bromobenzene. Why is it wrong? Look inside the ring. There are no double bonds or circle. Whenever you're doing an aromatic ring reaction, make sure you put the double bonds in there or do the circle, or I'll mark it wrong, because it is. I'll say it again. Remember to put in the double bonds, because if you don't, that's a cyclohexane ring, and you don't lose those double bonds. Now, the other thing I mentioned in the videos, and later on, you're going to do a lab with this concept, but if I had a group on there and I'm doing this reaction, where does the group that's already there, where does the new thing go? And there are rules that govern that. Since none of you are planning on being organic chemists, I'd rather spend more time on things later on, like fats and oils, carbohydrates, and proteins, than on what's called learning directors for electrophilic, nucleophilic, electrophilic aromatic substitution. And therefore, the only two reactions I can give you on a test is when X is either bromine or chlorine. Now, the next one is nitration. And when you take nitric acid, HNO3, and sulfuric acid, you put on a nitro group, NO2. Not NO3. People see this here. And when we do the lab, I'll explain how that becomes NO2. But for now, and by the way, that's the only reaction, because I'm not going to have something on the ring, because then I'd have to teach you about directors. Now, another one is if you take a benzene ring, react it with SO3, sulfur trioxide, and sulfuric acid, H2SO4, and you put on what's called the sulfonic acid group. And here it's SO3H, and you should know that. Now, I'll show you later on the ability to put a sulfonic acid group on a benzene ring. And the question you should ask always is, why am I learning this stuff? Well, this reaction allows them chemists, industrial chemists, to put a sulfonic acid group on a benzene ring, which is the basis for the main molecule in all your laundry detergents. I don't know about you, but I like having clean clothes. And all laundry detergents, or not all, but majority of them, have a benzene ring with a sulfonic acid derivative, something made from this, on there. Again, this reaction, since I'm not going to have anything on the ring, is the only reaction I can ask you on test number one or even the final. And finally, the last one, this is called Friedel-Crafts alkylation. I'll never ask you the name, but I honor Friedel and Crafts for their great creation. I don't know if you call it discovery, invention, that sounds better, of this reaction. And here you take an RX. R is anything with carbon and hydrogens. X in this case is chlorine or bromine. You need aluminum trihalide and replace one of the hydrogens with the R group. Now, listen carefully. The bond from the benzene ring to the R group is to the carbon atom in R here that had the halogen bonded to it. And let's look at an example. Sometimes when R is too big, you don't put it on top of the arrow. I went through the different ways you can write a chemical reaction in organic chemistry. So if we look at this reaction, the question is, give the organic product or products for the following reaction, 3 points each. So I have a benzene ring, that's different. Remember, when you look at a molecule, you look for what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond, and that gets your attention like that. If I look here, carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, whoa, carbon halogen, that's Rx. This is my R group. And I also have aluminum trihalide. Remember, X can be chlorine or bromine. And I replace one of the hydrogens on the benzene ring with my R group. So I have my benzene ring. Don't forget to put the double bonds in there. That's cyclohexane. I'll mark it wrong. Do you break carbon-carbon single bonds? No. So notice in my R group here, I have 1, 2, 3, 4 carbons. That R group better end up on that ring with 4 carbons. Which carbon has the halogen? The N carbon right here. So that's the carbon. I made that bond a little longer so I wouldn't run into the arrow. That would be bonded to the benzene ring. There are 4 bonds to carbon. And remember, on a ring, we don't show hydrogens, and that would be the product. Oh, let's have you have some fun. And I'll give you a chance to try this. Isn't it nice I shared a fun? And it's your turn. Give the organic product or products for following reaction. And when you're done, give me a thumbs up. I see a lot of thumbs coming up. We'll give everybody time to finish. If I were in a live classroom, I could just look around and I usually say, when you're finished, look up and smile. I can tell when students are done in the classroom. All right, let's do this. What's different? Ooh, a benzene ring. Double bonds give it away. Then I look at this molecule, look for what's different, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. Get your attention like that. Ooh, a carbon with a halogen. So that's Rx. And then I have this catalyst, aluminum trihalide. Remember, X can be chlorine or bromine. And this is Friedel-Crafts alkylation. Replace one of the hydrogens with the R group. The bond to the R here is to the carbon with the halogen in R, this carbon. So I'm going to have my ring, benzene ring. Don't forget to put the double bonds in there. That's cyclohexane. And I'll mark it wrong. You don't want that. And Do you break carbon-carbon single bonds? No. So I have 3 carbons here. My R group better have 3 carbons. The benzene ring, this bond, is to the carbon in the R group that have the halogen. This one. So there are 4 bonds to carbon, so I know how to put the hydrogens in, and I make isopropyl benzene. Now, there's one last thing I need to talk about, and that is, as you've learned so far, if you've watched the videos, I'm a synthetic organic chemist. That's what I got my PhD in. That's what I worked at in industry when I was working all the years in the chemical industry. And that means synthesis to make. And that's the fun part of organic chemistry. A lot of fun. Well, on test number 1, I'm going to have what I call one synthesis problem. And that's where you give the starting material, what are the reactants you would use to make a certain molecule. And that's what I did, except at a higher level, at my level, I was asked to come up with molecules at a certain price that solved a certain problem. Like, how could you make a better fabric softener? Yes, I worked in those areas. Later on, you'll learn about that in the videos. Ooh, coming attractions. So let's look at the following reaction or problem. And the question is, well, how do you find out what's the starting material? And this, for test 1, there'll only be one question like this and only one starting material. In test 2, I think I put 3 or 4 problems, and some of them might have more than one starting material, and I'll put 2 question marks. But how do you do that? Well, you look at the product. What did you make? What's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? Should get your attention like that. It always works. Oh, look here. I have 2 adjacent carbons, that means next to each other, and each one has a halogen. And right here, I'm reacting whatever we start with halogen gas. Remember here, X can be fluorine, chlorine, bromine, or iodine. Well, what do you start with? And you've got to know the general reaction, a double bond. So the 2 carbons with the halogens are 2 carbons in the starting material of a double bond. Do we break carbon-carbon single bonds? No. I'll need the room here, so I'll erase the, so I have 1, 2, 3, 4 carbons across. I have 2 methyl groups, remember that's CH3. Which 2 carbons have the chlorine? Those 2. Which are these 2 carbons, which would now be a double bond. Now I know there are 4 bonds to carbon. I can put in my hydrogens. Remember, a double bond counts as 2 bonds to that carbon. That's why the N carbon only has 2 hydrogens. 2 plus 2 is 4. Isn't the math hard in my class? Remember, you cannot use a calculator on my test. And that's the synthesis problem you should practice. How do you practice these? Go to my practice problems, take any of the regular problems from the answer key, cover the starting material, look at the answer and figure out what was the starting material. And with that, wow, it's a long evening. Time flies when you're having fun with organic chemistry with Dr. White. I'm done. If anybody has any questions, I'll stick around. If not, you've learned by now, gehen gesund is Yiddish for go in health, something my grandmother, Grandma Greenman, always said to us when we left after visiting her. So I'll stick around. I'll be posting this video, a video of this later tonight or early tomorrow morning, so you can go back and watch it if you want to. And with that, I'll say, okay, well, before I do that, let me ask one quick question. Give me a thumbs up if you thought this was useful. Well, thank you. Guess what? I'll do it again. And with that, thank you, Dorcas. I'll say, gehen gesund, and you know I do this stole that from Beverly Hillbillies Granny. Goodbye now, but I'll stick around if anybody has any last minute questions.